3 years ago, I asked the most unthinkable and crazy question possible. Are we the first generation that won't die?
What if the secret to a longer life is actually crawling right beneath our feet?
So what do we do?
Cells consume, Morty. Life itself is wrong, and that means death is right. But you can't side with that.
Deep inside every single one of your 37 trillion cells, there is a tiny molecular clock. And scientists believe that these clocks determine not just how long you live, but how well you age. These clocks have a name. They're called telomeres. And the story of what they are and what they do has led researchers into the chambers of human secrets of aging and potentially immortality. Telomeres may be the reason of aging, but the cause of it is something totally different.
The Nobel Prize for her discoveries at the molecular level of how the ends of chromosomes, the so-called telomeres, work. It's a fundamental mechanism.
Hello, my name's Elizabeth Blackburn. I'm in the Department of Biochemistry and Biophysics at the University of California, San Francisco. Now, if you looked at a cell which is just about to divide, and you looked under the microscope and you'd stained the chromosomes, this is what you would see. Now, if you look closely, you can see red spots. 2 red spots at the ends of every double chromosome pair. And these red spots are a molecular probe that's lighting up the telomeric DNA that's found in common at all of the chromosome ends.
Every time your DNA gets replicated, a small section at the end of each chromosome gets left out. So with every division, your telomeres get a little bit shorter, a little closer to critical threshold.
And think about it, like the protective caps at the ends of your shoelace, and those keep the shoelace or the chromosome from fraying. And when that tip gets too short, it falls off. And that worn down telomere sends a signal to the cells. The DNA is no longer being protected, sends a signal, time to die. So end of story. Well, sorry, not so fast.
So why does this happen? When your telomeres shrink past a certain point, your cells enter a state called senescence, like a zombie mode. They stop dividing, but they also don't die. They just sit there, secreting inflammatory signals that damage nearby cells. When you accumulate enough senescent cells, you start to see the hallmarks of aging. Slower wound healing, stiffened arteries, and even cognitive decline. Telomerase is essentially the antidote to telomere shortening. It rebuilds the ends of each chromosome after division, keeping it long. And certain cells in your bodies produce it naturally. Stem cells, immune cells, reproductive cells, because they need to divide many times without aging out. Studies in mice have shown that activating telomerase in aged mice actually reversed the markers of aging. Their organs rejuvenated, their brains sharpened, and their hair grew back. Researchers at Harvard's Sinclair lab made old mice young again using gene therapy that targeted telomere length. News articles ran wild, with headlines screaming, "Scientists discover the key of immortality." The billion-dollar wellness industry noticed. Today, you can buy telomere lengthening supplements, get your telomere length tested with a blood test, and find no shortage of longevity clinics promising to reverse your biological age by protecting your telomeres. So the obvious question, what if we switch on telomerase in all our cells? Could this reverse aging altogether? Before you get too excited though, doesn't this sound familiar? Isn't there already a cell in the body that has the capacity to never stop dividing? Yeah, that's right, cancer cells. Telomeres are correlated with aging, but correlation is not causation. Having short telomeres could be a sign of aging, but not the cause of it. Turning on telomerase across all human cells isn't just rejuvenating, it's also what cancer cells do. Tumors hijack telomerase to become immortal, so a blanket switch on of turn on telomerase carries serious oncological risks.
There's a new idea about aging, and that is that as we get older, genes are switched on and off in the wrong way. So when we're young, there's a beautiful symphony playing, but as we get older, the instruments, the orchestra starts to play willy-nilly and screw things up. So if we zoom into the cell, you'll see a chromosome, and if we stretch out the chromosome, that's the DNA, all twirled up there in grey. The pink blobs are proteins called histones that the DNA is packaged in. Red means the gene is off. The problem during aging is that chemicals come in and stick to the histones and turn the genes on. So that's what the green lights mean. This gene that should be off in the brain of my grandmother is now coming on. And that's a terrible thing. And this, what we call an epigenetic change, That's reversible. So let me show you how we can reverse it.
Now, a few things help to reduce these chemicals in the system that would go on to affect the histones.
Dr. Ivona Perchin at the University of Pennsylvania is working with a mysterious substance called sirtuin, a protein capable of delaying the aging process at the molecular level.
One of the best known studies is where mice that were fed a diet that was restricted in calories had significantly longer lifespans. One of the set of genes that were changed by restricting calories was one of the sirtuin genes.
One way to eliminate these chemical bonds would be to increase the expression of this specific family of genes called sirtuins. These genes are a code for a family of enzymes that manage cellular stress by detaching these chemicals from histones, leading to longevity. They also oversee DNA repair, control inflammation, manage how your cells produce energy, and most importantly, they influence the epigenetic changes that cause aging. The only problem, sirtuins are NAD dependent, which decreases as you age. You hear a lot of hype about NAD as this new miracle drug, but they all miss the point. Less NAD means less sirtuin activity, which means the chemical chopping and the DNA protecting enzymes go quiet and aging accelerates.
They're stimulated naturally when we don't eat and when we exercise. And if we eat a large hamburger, we shut them down again. This is not good.
Reducing caloric intake also increases the expression of sirtuins. So after all this research and effort, we've come back in complete circle. Is fasting really the end of the line? Luckily, no.
And we weren't looking at resveratrol. In fact, I'd never heard of resveratrol when we started working on it. Resveratrol was already known as what's called a phytoalexin. The story goes like this. It's a pretty funny story. And Conrad calls me one day and he says, are you sitting down? I went, I am sitting down. What's up? And he goes, we've got these strange molecules that may activate the enzyme. And then that was, of course, music to my ears because we didn't know that NAD could be used at that point. We were just on the verge of discovering that. But finding activators of enzymes is extremely rare. I think there's only a few examples in the whole history of pharmaceutical development. And when you find one, typically people call BS on you. But here was Conrad saying, maybe we've got something. So we tested it in the lab and we could repeat his results. Yes, it was an activator.
In the early 2000s, a new compound was discovered. It was called resveratrol, found in the skin of grapes and, as you may have it, red wine, which has the potential to activate this. Resveratrol attaches to these sirtuin enzymes and makes it churn through these chemical bonds much faster. So maybe drinking red wine is the healthiest option. But here's the catch. To get enough resveratrol from wine, you'd have to drink more than 100 glasses of wine a day. The human science around resveratrol is cloudy. High-dose resveratrol studies found to be interfering the benefits of exercise in older men. So resveratrol may not be the answer we're looking for. Immortality pills may not be on the shelves yet, but the research is pointing towards something profound. Aging is not simply inevitable decay. It may be a biological process that, at least in part, one day could be understood, measured, and potentially reversed. If you found this interesting, drop a comment below of what we should explore next. The science of aging is barely even scratching the surface yet.